All right, so why we're seeing this textbook is super important. It is because, for instance, first of all, we have a maximum subarray sum. So these solutions, all right, demonstrate how would you optimize the solution from O n cubics to O n. So the transition is O n squared, right? Okay. This is a big jump. This is a big improvement here. And as you can see, one of the USACO questions this is a generous one. The question, first of all, is we can loop through every pair of numbers, 1 to n, blah, blah, blah. It takes about O n qubits time, right? Okay. But the subtext of number two, it motivates this following O n squared, right? And eventually it is going to be O n. So as you can see, this textbook is super important. This handbook is really important. You got to read through it, right? Okay, so the sample questions is you want to find the maximum subarray sum. So subarray, it doesn't have to be consecutive, right? The largest possible sum of the sequence of consecutive data is in the array. So now we do have the definitions here. So that simply means this is considered to be a subarray, right? This is also a subarray. So the most naive is you put I right here, right? And then you also put a J here. And then you loop through the rest. And this is going to be K, right? This is going to be K. So therefore, it looks like it's -1 plus 2 and a plus, we have a GK method here, right? A function here. So at the next round, we definitely will shift the J forward, right? So that is going to be the middle loop here, right? So overall, it takes three loops to solve the problem, and it is guaranteed that you can solve the problem perfectly, right? Okay. And then let's check out these solutions here. All right. So the algorithm, a straightforward way to solve the problem is to go through all possible subarrays. So usually we call that a brute force, and calculate the sum of values in each subarray and maintain the maximum sum rate. The following code implements the algorithm here just like that. It starts with a 0 less than m, and the b starts with a, right, itself, and then that, and the sum indicates that declared in the middle loop here. And then we have the k loop here, right? Okay. You can use I, J, K, or A, B, K, or any indicator you want, right? Okay, there we go. And then subarray will be incremented by that, right? Good. So it is guaranteed that you can solve this problem perfectly by this. Okay. Um, so the visual demonstration is basically, firstly, you add this one, right? And then you add this one, right? And then you add this one here, right? And then you add this one here, and you add this one here, and you add this one here, and you add this one, and add this one here, and then it's done. And next one, you have this one here, and then this one, and this one, and this one, and this one, right? And then you have this one, this one, this one. So therefore, it's guaranteed that you can find all the possible solutions here, right? Good. Let's see that. So that's why you can see the algorithm starts with a 0, B is right onto A, and the K is onto A as well. So therefore K, so this is A, this is B, and this is X. K, as we can see, K starts here, right? And the full range is here, right? Okay, but in the first round, B is actually here, so it basically add itself, right? And next round, we'll go through this way. And then shift A forward, and the K starts here, and the K starts here, and the K starts here. So therefore, it's going to be like upside down triangle shape, right? Okay, good. And then so the variables A and B fix the first and last index of the subarray, and the sum of values is calculated by the variable sum. And then once again, let's check out um, um, the visual stuff here. So A and a B, the beginning and end, right? And a K will do the work in between, right? Da 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 da, right? And what if A is in different location? Yes, definitely it can be in a different location, right? And maybe right here. So case range is constraint always between A and B. So therefore it can accumulate the consecutive subarray rates. Okay, there we go. And then right here, what do we have here? Algorithm number two here. It is easy to make algorithm one more efficient by removing one loop from it, right? Okay. This is possible by calculating the sum at the same time when the right end of the subarray moves here. The result of the following code is here. So first we also need a outer loop to handle the work, right? And then so we have our inner loop here, right? Okay, so this is exactly the same inner loop here. And we can find the best or the optimal solutions right away, right? Therefore, we don't have to accumulate one by one by using the inner loop, right? So for instance, right here, what we could do is we simply just put A and a B here, right? Okay. So because a B is also traversing it, right? B is also traversing it. So you calculate the current sum. So apparently this current sum is going to be what? The current sum is going to be 1 plus 1 is 2, right? Okay. And the 2 compare with previous, all right? And we also want to compare with which one is bigger, right? Which one is bigger? And apparently the previous one is this part. And that is going to be uh 1 plus 4, which is a 5, right? And apparently we don't take this subarray, we take the previous subarray that is basically 5, right? So definitely we can definitely do that, right? Okay. So that's why the second solution works. Algorithm three, surprisingly, it is possible to solve the problem in one time, which means that just the one loop is enough. The idea is to calculate for each array position and a maximum sum of subarray that ends at that position. After these, the answer for the problem is maximum of those sum here. And right here, consider the sub-problems of, yeah, you see the sub-problem, right? So in the user code, you also see subtask. You also see sub-task, right? Okay. And to find the maximum sum subarray that ends at position K, there are two possibilities here. The subarray only contains the elements at a position K, and the subarray consists of a subarray that ends at the position K minus 1, followed by the elements at the K position K. So in the later cases, since we want to find a subarray that with a maximum sum, the subarray that ends at the position K minus 1 should also have the maximum sum, right? Thus, we can solve the problem efficiently by calculating the maximum array sum for each ending position from left to right. So remember, I calculate the previous position later, right, in the previous example here, such as the K minus 1 and the K, right? If you remember. So this is a 5, and this is a 2, and the P is a 5, right? And we have a maximum between current and the P. So yeah, this is basically the logic, right? Okay. And then we have this exactly the same. We use a single loop here, and we accumulate sum, right? The sum is going to be the maximum between the current K and the previously all the K and with the current sum, right? So this is a little bit like the prefix sum, a prefix the sum, a little bit, all right? A little bit like a prefix sum. Okay, and then we find the best by using that. This algorithm only contains one loop that goes through the input, so the time complexity is O(n). This is also the best possible time complexity because any algorithm for the algorithm has to examine all array elements at least once. All right, okay, there we go. So these are how would you actually figure out the solutions. All right, okay, and then right here, all of these here. So therefore, I want you to go over this old USQL question again, and I want you to absolutely do this question again, all right? Since this is a very important question. All right.
Oh, okay. Wait, in Python or